All right, welcome back. This is the Vintage Tech here. It's Christmas Eve, Friday before Christmas here, 2022. And I'm going to share with you a video repair of a low water cutoff control module for a boiler, a commercial boiler that we have at my work. And these modules go bad, and they have lots of surface mount components on them and a control relay. Basically what it is they use a probe inside at the top of the boiler that is probed right into the top of the vessel with a wire that comes over to the sensor, to the board. And the board is designed to detect the presence of water between the terminal of the probe and the ground of the vessel. And in this particular case, that's around 25 k ohms. And this module is designed to watch for about 25 k, and if that 25 k is missing, this module will sense that and open a relay and tell the boiler control to shut down. And it shuts down all of the bypasses, all of the safety controls and everything, and shuts the boiler completely off until the low water condition is restored. The high water, or the proper water level, is restored on the boiler. And so we have at least two of these that have gone bad on our boilers. And so I just decided, we did order a new one, got a new one, and I decided I was going to try to fix one of these because they're rather expensive. They run anywhere from $300 to $500 depending on where you can get them. And in fact, we ordered one of these from a manufacturer, from a company, and they told us that they wouldn't be shipping them until the middle of January. So we're not going to wait until the middle of January to get a boiler going. So we found one, thankfully, and we got the boiler running. But now we have this other module that we've been reverse engineering, and I'll zoom in on this schematic a little bit later. But we reverse engineered or drew the schematic basically in studying the module, and finally figured out the problem. So I'll work through the troubleshooting process in the video, and spoiler alert, we did get it working after several hours of troubleshooting. This is a practical lesson on questioning your assumptions. As an electronics technician, the more experience you get, the more you make assumptions in your repairs, and you say, well, I've never seen an LED go bad on a circuit like this, it can't be the LED. Or the guy told me he checked the fuses, so there's no reason to check the fuses. Or I don't believe that I believe the wiring is correct according to the schematic, so I'm going to assume that that's correct. Those kinds of assumptions will often get you into trouble. And that's what this story is. That after a lot of troubleshooting, we kept coming back to the assumption, or coming back to a bad LED, which was in series with the relay coil. And got tested with the scope and with meter and all of this, and we just finally came back and said, you know what, even though the LED glowed slightly, just a little bit, maybe the LED's bad. Sure enough, that's what it was. So we replaced a couple of components that were popped, and we finally replaced the LED, and we got the module working. But we're going to work through that in the video here, and hopefully it'll be of some help, or if nothing else, some entertainment value to you technicians out there. Well, what we have here today is a liquid level control board for a Kelly Patterson boiler, commercial boiler. And this device senses the boiler water presence, and if it drops below a certain level, it will trigger an alarm, quote unquote, inside this board and disconnect the boiler. So it's an important safety feature, and these boards are very difficult to find. They're on uncertain back order for mid-December, and this is mid-November, and I don't know when we're going to get them. But basically, the way this works is that there's 120 volts here on these two terminals, line 1 and line 2, and that drives this transformer. And then the transformer secondaries are rectified here with the diodes and filtered and so on and so forth. Then there's a low water cutoff sensor that's just a probe that sticks into the boiler vessel and measures resistance based on between the low water cutoff probe that is into the boiler vessel and the ground lead of the vessel. So there's a ground connection here and a low water cutoff vessel, and the resistance between these two terminals triggers this circuit in here. Very simple. And then there's the terminals for the relay, the common terminal, normally open, and normally closed terminals, and you can see they're identified there. So that's all there is to it. So if the resistance is not correct on these terminals, between these two terminals, based on the amount or based on the presence of water touching the tip of the probe, then that turns this circuit, turns this relay, opens this relay. And if this relay is open, then because of the normally closed and common terminals, then the boiler will not fire. It goes into an alarm condition that the low water cutoff circuit is engaged. So one workaround temporarily to confirm that this board is bad is to just take the the common terminal and the normally open terminal and short them together and then fire the boiler up, and the boiler will run. Well, then you know that this circuit is bad. Either the probe is bad or this circuit is bad. So we're going to see what happens here. I'm going to hook 120 volts up to the circuit here, and if we have the right resistance between the low water cutoff and the ground connection here, we should get a red light and the relay contact should close. And so we're going to see what happens there when we hook this up. Initially, this board would light up and work for a few minutes, and then after just a couple of minutes, it would go into fault. The light would go out or go dim. I'm not sure why that was happening. And the relay would drop out, and then it would throw the computer on the boiler into alarm. So that's what we're going to do. We're going to hook the power up here with a cord, and we'll get some contacts put on this and hook it up here. And then we'll hook some resistance up here, test some various resistances to simulate the water probe, the low water cutoff probe, and then we'll do a little further troubleshooting as we go. I want to go through this schematic. This is a pretty rough schematic of what the board has. We have the low water cutoff probe right here, and comes in. We have the 124 volts AC transformer, center tap transformer, and then the ground plane, which has a separate ground connection just for the probe, and it's also tied into the power supply ground. So the resistance between these two terminals, the probe itself and the ground, create a voltage divider circuit. There is I believe it was 6 volts. If I can get the camera to focus. There we go. 6 volts AC across the terminals of the low water cutoff and the ground. And then there's a voltage divider here and rectifiers that go into an amplifier circuit and feed part of the op amp or comparator. There's a dual comparator in one chip, as we saw in the pictures there. So there's a reference voltage and an input voltage on the comparator, and those two are compared. And there's a timer circuit here that monitors input or disconnect of the low water cutoff. And when the low water drops, or if there's a surge of drop in the water level, it'll start a countdown. 5 seconds basically is what the timer is, between the RC, the resistor and capacitor, and the comparator monitors those levels, and then that voltage level, and turns on. If those are acceptable, it sends a signal through this path, through this little transistor that drives the LED and the coil, the relay coil. And there's an FET that closes the ground side of that circuit. So these two work together to assure that the relay is being controlled. I suspect that if this transistor were to short, the relay would stay turned on all the time. So it could be a fail-safe, because it is a safety circuit. Could be a fail-safe that they have this FET that's running here to pull the ground leg of the relay. So as long as the relay is energized, these contacts are closed, and the common and the normally open contacts are closed when the relay is energized, and this goes on to the boiler control module. So that's how it works. There's a reset pin somewhere on the board, that might be it right there, that is not used, that you can test the functionality of the board, and those terminals are not used. I think it might be one right there. Yeah, I think it might be test 7 there. Anyway, that's what it's all about. This was another drawing, a little bit tighter view of how the unit is set up, and with the op amp here going being held high, dropping to low to turn this transistor on. So that's how that works. All right, let's just take this one step at a time. We're going to fire this up and see if we get any indication on the light. So be watching this, and I'm going to turn the power on the unit. Okay, so we got 110 volts, 120 volts, excuse me, on these terminals now, and no light, which we would expect because there's no resistance on these two terminals. So let me turn the power off, and we will hook up resistance on these two terminals. Okay, I want to do one further test here, just for safety's sake. I have the AC on, and I want to check and see what kind of voltage I'm running across this resistor, just in case I don't want to blow up my substitution box here with a lot of high voltage. So you can see we've got 12 volts AC. Yeah, 12 volts AC on those terminals. So it passes voltage through that resistor and is checking for current / resistance, the proper current and resistance on that low water cutoff probe. So now what we're going to do is disconnect the meter, and we'll connect the resistance box up. Now, someone had told me they thought that it was looking for needing about 50k ohms on the terminals in order to fire the unit up. So we're going to have to test that theory. We'll also we can determine how much current is flowing with 12 volts AC on 50k. We'll be able to determine what kind of current is flowing through that sense circuit. So let me turn the power off. And since we're working with 120 volts, I'm just confirming constantly that we don't have high voltage. And when I say high voltage, I'm talking about 110 volts, so that I don't electrocute myself. And so we'll hook up the we'll hook up the resistance box to that and to that. Let's confirm that we have, before we hook it up, let's confirm what kind of resistance we have. Okay, 50k ohms, which is what we have set here, 50k. So that's good to know. All right. So let's hook that up, and let's see if we can get this circuit to fire up. Now, if the circuit was working correctly, and if we have the right resistance, and we're going to experiment with different resistances until we can see what kind of current we need. But we'll see what we get here with these connections hooked up to the low water cutoff connection. So here we go. We're going to turn the power on. We don't have a red light. Actually, we have a dim. Now I can't tell if it's, let me see if I can. No, we don't have any light there. So we have a problem with the circuit, because that should be enough current to fire the latch circuit. So we'll turn the power off. We're going to drop this to 25k. Okay, so we got 25k, 24, 25k. See if that makes any difference. And let's just, for giggles, let's monitor the voltage and see what kind of voltage we're getting across the resistor now with, okay, so ready? We'll turn it on. 120 volts. Okay, we've dropped it to 5 volts, and we have a red light. A little bit. See it? Flickering. So it's trying, but it's not enough to click this relay. Okay, so let's do the math and figure out how much current is currently flowing through the substitution box, because we are dropping down to 6 volts AC, and it's trying to engage, but I don't want to burn up. These are only half-watt resistors, so I don't want to burn up the substitution box. So let's turn that off, and let's do the math real quick here. Okay, you recall that E equals I times R, the Ohm's law. So voltage equals resistance times current, or current times resistance. So if we want to calculate for current, we take voltage divided by resistance. So we have, 12 volts divided by, what did we say, 25,000 is 4 microamps. So, or 480 microamps. So it's super low current. All right, so we're not going to burn up the resistors at this case. So let's drop it. Let's drop the resistance to 12K. We'll half the resistance. And what would that be? 12 volts divided by 12,500. 12 volts divided by 12,500. Okay, so we're still not even a milliamp, almost a milliamp. All right, so let's do that. Power is off on the, there's no power. So let's change this to 1,000, 3, 4, 500. We said 1,250, didn't we? 1,250. 1,250. Okay, and we can confirm that with our meter here. 1,100. Let's take it off of the thing. Yeah, there's 1,221. Okay, close enough. All right, so now let's switch this back to voltage and turn it on. Okay, we got a dim, let me turn the light off so you can see it. We got a dim LED, but it's still not firing up. And we've dropped our voltage on the terminals down to a 0.5 volt. So we've got an issue. Well, let's go the other way just for giggles, and let's go up above 50K. And let's say it's going to be 100K and see what it's expecting. So here's 100K, and we'll confirm that resistance. 100K. All right, now voltage, 100K. Turn on. Appreciably 0 volts. And LED not lighting at all. As you can see, it's not lighting at all. Okay, all right, so we don't know for sure what is what's causing this, but that's the problem. The board is not initializing, if you want to use that word. That's a little bit of an overcomplication, but that's exactly what's happening. The board is not seeing the probe, and for whatever value we're using for the probe. So I'm going to unplug the power. It's already turned off. I'm going to unplug this power, and we're going to do some checks on these caps. Those are the first things that are suspect. And we could do some voltage checks, and we will. We'll do some voltage checks on the secondary and on the diodes here to see if we've got some kind of a problem with incorrect voltages on the power supply. So let's check these 3 caps right here, the bigger ones, and see if we've got a problem with them with our ESR meter. And we'll get that on the screen. I'm going to move this over. Okay, good. And on this ESR meter, we have to make sure the caps are discharged, or it'll burn up the ESR meter. So we'll short the caps, that one, and that one. And there's a surface mount cap here. on some of these boards they put a through the board cap instead of a surface mount. But, and we'll check this one. I think we can check this one. I don't know what value it is. I'll have to look that up. It says 100 microfarad. I think that's what that is, but we'll check it, because 25 volts, that seems a little high. But we have a 4.7 here. So let's check the 4.7 cap. Okay, that cap is definitely bad. See that? I'm checking it. You see the meter? It's either open or, you know what, it could be that I've got some conformal on the terminals there. So let me pierce. Yeah, there is some conformal on that board. Let me pierce that, because I probably am just insulating it. There we go. Yeah. So I got 2 ohms ESR on that resistor, on that capacitor. And then we'll check this one. And it's good. It's good too. So the capacitors, those 2 capacitors are not bad. And we can check this surface mount cap. I have to penetrate the conformal. And it's good too. So the 3 electrolytics, and there's one more down in there, but it's a surface mount and probably not relevant, may not be relevant. All right, let's check these diodes. Okay, open. Oops, remember our conformal. Okay, that one open that way. You should have near short this way. Okay. Nope, that diode is open. I'll check it with a regular meter, but I'm going to check it with the ESR meter, because this is designed to be able to check. That one says it's open. That direction. Okay, open that direction. All right, let's check it with a regular meter here. Well, we can check it with our fluke. What am I doing here? Let's get the fluke and check it with the fluke. Diode mode. Okay. All right. Let's see what we have here. All right. Conduction that direction. Should be show open this direction. Okay, good. Now this one should be conducting the other direction. Huh. If I'm getting to the terminal there, and I'm not confident that I am. We can get a decent connection. There we go. Goes 1/2 volt. That's good. So it's telling us that the diode is not shorted. There we go. 1.5 volts conducting the other way. All right, we got one more, at least one more diode right up in here. He's right there. And I don't know that I can get in there. Let's test it with the ESR. And we'll puncture that conformal. Okay. Trying to scratch off the material there. Okay, I got that side in. Okay, I just did a temperature test and on the board to see if there were any components that were warm, and nothing showed up. That is, nothing abnormal showed up. So now we're going to leave this on 10K or whatever, and we're going to test our power on the secondary, and we can do that from this side. Got a ground connection here, and we'll test our secondaries right here. There we go. All right, well, got to get the meter set right. 116 volts input. Okay, and now let's check the secondaries. 14 volts, 15 volts AC, 30 volts. So we've got 15 volts AC, on one side to center tap, and from the other side to center tap we have the same voltage, and 30 volts. I suspect that it's considered 24 volts, but anyway, 30 volts. All right, so our transformer's okay, at least if that's what we're expecting to see there. Now I got to remember, I've got this still plugged in, so I got to be real careful. I want to move this around, and I want to check the power on the diodes to see if we have any. Got to be real careful right there, because that's 120 volts. Okay, we can unplug the resistor, and let's just see what we have across here. Be DC. Be better to test these things with a scope. You could see the waveform and read the voltages. Okay, 18 volts. Okay. Turn the power off. All right. One other simple check we can do is to see if the relay thinks it should be engaging. The relay contacts for the coil are right here and here. And so let's just do a check to see if the relay clicks. $12 volts. It's a 12-volt relay. 12-volt DC. All right, we'll turn the power on. All right, we don't have any power on the relay. No call for the relay to be on. All right, let's turn the power off. Let's put the resistor in to the ground and to the probe. Okay, and let's hook this back up to the coil. All right, ready? All right, we had a little bump there. All right, we're going to bump this to 30K. All right, and there's a chance that the circuit is a latch circuit, which means that once the power is on, it will stay until it's reset. Okay, we have just some residual DC voltage there, 130 milliamps, which clearly is not enough to turn on the relay. All right, let's do a little bit of tracking now. Okay, I was able to discover that the comparator is not driving the circuit to turn on the relay. Alrighty, well, we're going to replace this dual op amp right here, and I believe this is acting up, and so we're going to remove this chip. So we'll put a little bit of flux on the chip. I've got some flux here. And then we'll put some low temperature This is low temp chip quick 4.5 chip removal alloy, and it's a low temperature solder basically that keeps the chip hot at low temperature so that you can remove it. So I'm trying to get the camera view in here. So we'll flow some of that in there across the pins. There we go. There we go. Flowing across those pins. And we'll lift the chip off. We'll use some good cam wick here and get rid of all of this. Okay. And got some liquid flux here. Flux it good. I'll soak this Chemwick in flux. There we go. There we go. A little bit right there. Okay. I got some of the flux remover now. Zoom out here. Alrighty, nice and clean. Okay, we've got our new chip right here, and some super fine solder. Alrighty. One thing I've discovered about working with surface mount is that it's a real test of your patience. When you have eyesight issues and a lack of steady hands, it can be a real pain, but just requires a lot of patience. Alrighty, well, we've got the comparator put in, and I want you to notice something here. If you'll notice, I was doing a little cleanup here. The chip is turned just a little bit to the left, but I believe the solder connections are solid, and so I'm not going to try to center that chip any better. But look right above the chip there at R15, and then notice in the bottom right hand corner of the screen, if I can get it adjusted here, R15 is missing. There's solder blobs there, but then I'll zoom in down and over into the bottom right hand corner of the screen. See that 275? That 27 meg resistor, I bumped it and desoldered it, and it fell in, so I'm going to pull it out, and it fell down in there. I'm fortunate that I discovered it. You can see the conformal glue, what a mess that stuff is to work with. So I'm going to pull it out and clean the board up and resolder that resistor onto its proper place there at R15. Alright, well, I fiddled with the 275 chip resistor here and finally got it positioned and tacked in and soldered and squared up nicely. But so I won't belabor the point here, but it does take some work with the microscope to get everything positioned and held into place while you tack it in. So eventually I got it squared up nicely and resoldered. All right, we've got the comparator put in and replaced that chip and resoldered 2.5 meg resistor in the board. So let's fire this thing up, see if it works. We've got our simulated water level here with 25K resistance, which is what the board specs. Looking for 25K resistance on these two terminals here, and so let's see what we get when we fire the board up. Well, after firing it up, we still didn't have any power on the relay, so I tracked it down to the driving transistor was shorted, and so all the terminals, emitter to collector, collector to base, and so on and so forth, were all shorted. So we're going to have to replace that chip transistor. Okay, I'm going to put this transistor right there, and then I've replaced the op amp, the comparator right there, and a 27 meg ohm resistor, which you can't see, I'm sure. There we go, right there, R15. So I've replaced the comparator, and now I'm getting ready to put this transistor right here. So I can't hold the camera and solder and all that at the same time, so I'll come back after I get that soldered in. Okay, we got a successful repair here finally. And Jesse and I have been troubleshooting this for hours, and let's see, we replaced the transistor, and we probably shorted that in testing the circuits. We might have shorted that transistor that drives part of this control circuit. Then you've got this comparator, which went dead somewhere along the line, and this FET went open. So the FET drives, I think we've got this right, the transistor drives this LED, which is series connected to the coil of the relay. And it took us a while to figure out that we had power all the way up to the LED, and we thought we saw the LED burn a couple of times, so we never even considered the fact that the LED might be open. And sure enough, question your assumptions, right? So we have this driver, and the power goes through the LED into the coil of the relay. What we discovered was this LED is open, and so we had power here on the transistor, had power on the FET, and as it turns out, this LED was open. So we replaced a transistor and an FET and a comparator. Probably had we just started with the LED, we may have found that was the problem. Although I had the LED glowing slightly when I changed the water sensor resistance, which according to the documentation, this particular board requires 25K resistance to simulate the water level. Here's the water sensors, by the way. And so they detect to ground to the input of this circuit and there's a 5-second delay, so it's working great now. And when the water level is up, circuit comes on, LED turns on, and the relay snaps, and everything's good. So let's simulate that. We're going to turn the power on right now, and we've got power and the relay clicked. If I disconnect or simulate a low water condition, after about 5 seconds, it's disconnected. 5 seconds, the water cutoff fails, low water cutoff. If I reconnect the water or refill the water, the LED comes back on and the LED re-engages the circuit. So I'm going to disconnect again. 1, 2, 3, 4, 5, and it goes out. So there we have it. Leave your comments or questions in the below if you have any questions or any thoughts.